Hello, sir. Naveen Shankar, sir.
Yes, sir. Hello.
Okay, sir. Shall we start, sir?
Yes, sir. Yes.
Okay, sir. Thank you. So, very good morning, participants. So, today, day 6, after 2 days, no more class. So, again, we'll continue the FDP. AICT sponsored 2 weeks online faculty development program on emerging trends and challenges in VLSI mixed signal processing for person Mr. Naveen Shankar, Field Application Engineer, Intable Technologies, Bangalore. Given the topic of design of SER based data converter using Cadence and EDA tool. So welcoming, sir.
Yes, sir. Yes. Thank you.
So before going to session, small introduction about our today research person. So introduced by our Mr. Bhaskar.
Sunshine is a welcome thing. It brings you a lot of brightness. This way, I would like to give a short intro about our resource person, Mr. Naveen Shankar. Mr. Naveen Shankar with Technologies, Bangalore since 2017. His roles includes a logical and physical synthesis, PNR flow consisting of a various steps such as a floor plan, power plant, sanity check placement, clock tree synthesis. Having experiences of 3 years in the field of application engineering for EDA products. He has supported on some of the design related queries at different levels like OTL design, OTL synthesis, physical design, physical verification in a PDP. He is also trained in the AC physical design and custom IC design with hands-on experiences in a back-end design too, including a routing, static timing analysis like OCR, TPPR, multi-cycle path, and a physical verifications like a DRC and LVS. He acted as a chat person, delivered special lectures in various conferences and various funding programs. In this way, now like to our resource person, Mr. Navin Shankar. Please, sir.
Yes. Um, Thank you all. Thanks for the introduction, sir. So let me share my screen first.
Yes, sir. You can share your screen, sir.
Yes, yes. Is my screen visible, participants?
Yes, sir. Screen visible, sir.
Yeah. Okay. Hope I'm audible clearly.
Yes,
So
sir.
I welcome all of you for today's session on emerging trends and challenges in VLSI mixed signal processing for fourth industrial revolution in association with Kongunadu College of Engineering and Technology. Myself, J. Naveen Shankar, field application engineer for Cadence from Interpol Technologies, Bangalore. Uh, and I think you must have heard about me just a few minutes before. So, without much delay, let us move into today's session. And before getting into that, basic guidelines for all the participants. Please keep your mic on mute and webcam turned off throughout the session. Meanwhile, in case if you have any queries, you can let me know on the chat. Even if you have any clarifications in between, you can just unmute yourselves and let me know your queries. Okay. And towards the end of the session, we'll be having queries Q&A session. Okay, maybe last 15 minutes or last half an hour. And you can also post your queries during that time. Okay, so let us move into the agenda that we are going to discuss in today's session. We'll start about a brief we, we'll start about a brief introduction on N-tuple technologies and cadence, and then we'll move into what is an AMS design flow. Okay, and then we'll be explaining the AMS design flow with a small example of SAR ADC. And before moving into the illustration, we'll have a quick look and on the background for SAR ADC. And then we'll move into design illustration, which includes schematic design and then functional verification of that, and then each and every block. Okay, if you go into SAR ADC, you'll be having different blocks. Let us have a look at how each and every blocks are designed. Okay, and then functionally check whether everything is responding in the right manner or not. Okay, and finally we'll go into the design flow on OrCAD PSpice first, and then using Cadence. Okay, so since we are talking about Cadence, what are the tools that we are going to discuss? Because you have n number of IC design tools that are available with Cadence. Out of that, which are going to be discussed during today's session. Okay, so we'll be discussing about Virtuoso, Spectre, and AMS. Okay, so let us move into a brief introduction about NTFL. We are a design service, product, and engineering solution provider in cutting edge technologies, which includes aerospace and defense, public sector companies, and automotive companies. And then we also work closely with research labs. Along with that, we also provide on-site and online training programs, as we are doing right now. And then uh, out of nearly 600 to 700 customers all over India, okay, more than 500 customers are from academics, okay, at engineering colleges, leading engineering colleges. So we have our foothold on academics also. Okay, and we are official channel partners for Cadence and Ansys. So along with all the support, we also work on these domains. Okay, mechanical, computational fluid dynamics, electromagnetics, systems, semiconductors, e-mobility, PCB designing and prototyping, 3D printing, indented test, vector network analyzer. We also manufacture our own vector network analyzers. Okay, along with that, we also work on RF solutions, cyber security, Internet of Things, and power electronics. And we also have um, our own power measurement uh, kit. Okay, power measurement device, which is widely used across industry as well as institutions. Okay, bird's eye view of NTUPL. We were incorporated on January 1st, 2010, headquartered at Bangalore. We also have regional offices in Delhi, Pune, Ahmedabad, and Hyderabad. Uh, the total number of offices for NTUPL across India are 13, whereas the team size is over 130. Okay, here it is given as 135. Okay, but it is well beyond that. Okay, so if we are talking about customers, as I have already said, uh, most of them are academicians and um, uh, research laboratory customers like DRDO, um, DRDO, Bell, ADE, etc. Okay, and the staff split. Okay, the number of technical people, okay, who are associated with NTPL are far more when compared to the sales team and administrative team. You can have a note at that. Okay, so we have partnership with some of the leading tool providers who not only work with industry alone, also with institutions, because nowadays people who are recruiting young engineers don't have the time to uh, get them recruited and train them on their tools. So they want people who already have an idea of how the tool works or what are the aspects of the tools. Okay, so uh, because of that aim and because of that motto, we have a strong partnership with ANSYS, Anritsu, Vanguard, Cadence, OrCAD, MITS Electronics, which is for PCB design and prototyping, and then Nivety Systems, Nanatom, EOS, Intuple, eMobility, Semicron, and XLVLSI, especially for training programs. Okay, out of that, we are official uh, channel partners for academics for Cadence and OrCAD. Okay, along with that, ANSYS also, ANSYS and Ritsu. Okay, so a brief introduction about Cadence. Cadence, as you all should be knowing, is a pivotal leader in electronic design, building upon more than 30 years of computational software expertise. So, for which domains are these softwares designed or softwares made use of? Okay, mainly for solutions. Okay, mainly for solutions that include semiconductor and systems. Okay, so right from the scratch, how to design a circuit on silicon chip, and how to fabricate it, and what would be the results that we can expect out of that fabricated design. And in case if everything is fine, okay, what happens to the taped out design? Okay, everything will can be checked out well in advance. Okay, even before you tape out your design. Okay, because it includes, we have all sort of libraries and tools that will help us in checking out the data, cross verifying the data. Okay, so the customer base for Cadence includes consumer electronics, hyperscale computing, 5G communications, automotive electronics, aerospace, industrial, and health. Okay, and since ICs are involved in almost all the fields as well as in our day-to-day life. Okay, uh, it offers broadest and most integrated end-to-end solutions for IC design, starting from silicon design creation, simulation, implementation, sign off of analog and digital circuits, off the shelf design IP and IC packaging, which includes machine learning enhanced EDA tools and machine learning enabled EDA flows. Okay. Okay, Cadence is providing solutions across the industries and for a wide range of applications. But what are the tools that are provided by Cadence, and which helps us in what? Okay, so that is what is listed out here. Okay, so when you are trying to design a circuit, okay, an analog circuit, we start with virtuoso. Okay, we start with virtuoso. So why and how virtuoso helps us? Virtuoso mainly helps us in schematic capture. Okay, before even before you fabricate your design on silicon, or even before you take the design on silicon, okay, you'll work it out on paper, right? Because based on the data that you receive from the customers, okay, so you first start designing the circuit. Okay, rather than directly jumping into the silicon wafer and fabricating everything. Okay, it is always better to first design on paper. Okay, but how do you, okay, you have designed everything, but how do you cross verify even before you move into the silicon wafer. Okay, you need some sort of software, right, that can help you in identifying what are the issues, how can they be overcome. Okay, so for that purpose, what we can do is we can make use of the EDA tools. Okay, so EDA tools will help us in checking out what can be the expected result. Okay, and we can compare those results with the theoretical concepts. Okay, and check, just cross verify whether we are able to achieve those results or not, or how can we achieve those results. Okay, so that is the reason why we have virtuoso, and then we have spectre. Okay, okay, you have designed the circuit and you have captured it on the tool, but how to check its functional behavior? You have to simulate it, right? So spectre is a simulation engine, okay, that will help you in simulating any type of design, let it be analog, RF, or mixed signal design, and across technology nodes, not only for 180 nanometer or 230 nanometer, etc. It can also help us in working out designs on advanced technology nodes like 16 nanometer to 5 nanometer, etc. Now the recent development is 5 nanometer, right? So it also helps us across the technology nodes and all these tools. Because why? Because it is marked for the entire set of tools, or it needs a combination of tools, right? The same tool cannot provide you with all the aspects. Okay, you have different tools for different applications and for different needs. Okay, so all these tools will help us in analog or RF design, mixed signal design, etc. Okay, and then once you have checked for the functional behavior of the circuit, okay, you need to go into the layout part, because you need an idea of how it looks like, how your design will look like on the silicon wafer, right? So for that purpose, you have the virtuoso layout editor. Okay, so what is a layout? As we move forward, we'll have a discussion on what would be layout. Okay, so once you are done with the layout, you need to check, or you need to cross verify whether whatever you have captured in the schematic is what is available in the layout also. Okay, so for that purpose we have tools like Ashura, okay, Ashura or PBS, etc. Okay, so once these things are done, once you have checked for the entire flow, okay, you go for the fabrication. Okay, and you enter into the packaging phase. Okay, so for packaging you have tools like Allegro and Virtuoso. Okay, so once packaging is done, you move into board level testing. Okay, so for board level testing and also for security analysis, you talk about signal integrity and power integrity, right? So for those kinds of applications, you have tools like Allegro or PSpice or CAD and security. Okay, and then in case if you wanted to make use of the blocks, or you wanted to design some modules for digital design. Okay, so for example, in your digital module, you might be making use of AND gates or flip flops, something like that. Okay, so how will that be designed, or how are they designed? Because when you are trying to work on digital designs, it is just like calling. Okay, you will write a program and the functionality will be called from the library that is present already. Okay, so for that purpose, what we are trying to do is we'll design everything. Okay, we'll complete the circuit or using a full customized design flow, and then take it over to semi customized design flow. Okay, So for that you need some sort of connectivity, right? So library files, the liberate library files provides you with that connectivity. Okay, so for generating those library files, you have tools like liberate and variety. Okay. Along with that, not only with the analog and RF circuits or mixed signal designs, it also provides Cadence also provides support for photonics based circuits and board level design and testing, and also for advanced packaging techniques. Okay, and to test the circuit after completing the packaging part. Okay. So this is about the solutions that are provided by Cadence for custom IC and PCB design. Okay, PCB design as well as fabrication. Okay, okay. We were talking about analog design. Now, what about digital? Okay, before we come into mixed signal, let us check what are the solutions provided for digital design. Okay. So for digital design, okay, we start with the design entry, right? So for design entry, using any of the HTML languages, you make use of the tool called Incisive. Okay. So what Incisive does, we'll check it out as we move forward. Okay. Once you have done the design entry, okay, you move into the next aspect. Okay, you have written a program, but how do you get a circuit out of that? How does the library understand what it does, and how does the library uh, get an idea of what is going to be the functionality? Okay, so for those aspects, you try to convert the program into a block level or module level design. Okay, so for that conversion, you have tools like Genus, Modus, Conformal, okay, and Stratus. Okay, Genus and Stratus is used for the design creations. But what about Modus and Conformal? And they are also listed out under design creation. Uh, why is that mentioned under design creation is because modus is used for the process called DFT. DFT in the sense it is designed for testability. So why do we go for design for testability? Especially because when you complete any sort of design, there may be circumstances, there will be circumstances where your circuit might give you the exact result what you're expecting, and they might provide you with the result that is also faulty. Okay, so in case if it is providing us a faulty result, so what kind of result it is, to identify what kind of result it is and how to analyze or how to rectify those things, or in case if you are willing to if you are looking to test the circuit. Okay, so what can be done? So you can include some fault models, right? So you would have heard about stuck at zero fault, stuck at one fault, built-in self-test. Okay, so you can induce some faulty circuit and check whether your design works accordingly or not. Okay, because you are inducing the fault, so you should be aware of what might be the result, right? So for that purpose we use the tool called modus, and then after each and every step you try to check out or you try to cross verify the netlist files. Okay, how to get a comparison report, because some circuits might have minute changes, but in some circuits you might have vast changes. You cannot go through each and every line of your netlist file because it will be time consuming and it will be tedious also. So you have tools that can compare the netlist files and give you the report of whether both are matching or whether there are some differences. If there are some differences, what are those? Okay, so conformer provides you with that kind of report. Okay, and then once you're satisfied with everything, okay, you'll be going for the physical representation of your circuit. Okay, and with the digital design for physical representation of the circuit, you have the tool called Innovus, and it is Innovus implementation system. Okay, and then you have the tool which can be called as sign off tools. So why we call it as sign off tools? Because uh, once you get the report, okay, that is going to be the result that you will expect, that you can expect out of a fabricated circuit. Okay, 99% that will be the same result that you can expect out of a fabricated circuit. Such is the standard of those kind of tools. You have timing sign off tool, which is tempus, power sign off tool, which is voltus, and then you also have tools for physical verification, which is quantus. Okay, so now all these things are listed out under electrical sign off. And then for physical sign off, you have a tool called Pegasus. Okay, and all these tools work hand in hand. Okay, it is not like you can only move into the next process after the current process, not like that. Simultaneously it works simultaneously. It doesn't wait for results from other stages. Okay, you can get ready with the blocks, then you can interface, you can connect them, and then connect them or interface, you can provide the interface and then go for the circuit completion. Okay, so upon going for circuit completion, you can also cross verify the results whether they match with each other. Okay, so this we call as parallel processing. Okay, rather than waiting or sitting idle until we get the results, it will be better if we work on our stage and come out with the results. Okay, so that you can save some time. Okay, so that is why we always prefer parallel processing. Okay, and all these results had to be exactly uh, accurate, right? Accuracy is more important. Accuracy and efficiency is more important, and that is the reason why it is one of the industry leader in semiconductor design and testing. Okay, and it also optimizes your design. You need not redo the wiring manually. Okay, you have the tools, because semi-custom IC design or digital design involves millions of gates, right? You cannot keep on digging at micro details for each and every errors. Okay, so uh, the tool takes care of everything. Okay, it optimizes, the tool itself will optimize your design so that you achieve the best results. Okay, so these are the solutions provided for digital design. Okay, now coming into the mixed signal. Mixed signal in the sense it is a combination of both analog as well as digital, right? So what are the solutions that are provided for mixed signal design? So in case of when you're talking about mixed signal, you have two options. One is analog on top and the other one is digital on top. Okay, so it depends on the base type of design. Okay, so if you have the base design as a digital, then you'll be having the top level design as analog, and when you have the base design as analog, you will be having the top level design as digital. Okay, so that is where you have the comparison of analog on top and digital on top. Okay, so what are the tools required for those things? So if you are going for a mixed signal design implementation, okay, so you tend to work on the Cadence platform for analog. And then for digital, you tend to work on Innovus and combine both of them. As I've told you, it is all the tools are interoperable. Okay, they communicate with each other well, and they generate the results required by those respective tools. Okay, so that is why we are being telling you, we are repeatedly telling you that they are interoperable, and they complement each other very well. Okay, so in case of verification, uh, you have a process called UVM. Okay, that is a part of digital, right? So for any type of mixed signal design and verification, you have to work on both analog as well as digital. And you when you go for industry, you have separate tool for them for working on those. Okay, so what are the platforms that are required? Virtuoso for design implementation, Spectre for verification on the side of analog, and when it comes to digital, it is uh, Innovus for design implementation and ZDM for verification. Okay, so then we come to the value added services that are provided by Cadence, starting with Cadence Online Support. Being the academic channel partners, we also provide online support along with the Cadence. Okay, and Cadence also provides you with the example designs and step-by-step process along with screenshot of how each and every step looks like on the tool. Okay, for that they have created some example designs and along with the manual. Okay, so those are called rapid action kits or rapid adoption kits. Okay, and then they also provide you with generic PDKs that are Cadence provides PDKs that are not uh, used for fabrication. Okay, it is only for learning purpose, but Cadence supports all the industry standard or fabrication, the foundry provided libraries. Okay, Cadence supports all the libraries. Okay, and along with that, they also provide some training guides. Okay, in order to get accustomed to the tools, and then also provide training programs as per the requirements of customers. Okay, whichever field or whichever module in which you require the training. Okay, based on your area of interest. Okay, so these are the value added services that are provided by Cadence. Along with Cadence, since we are the channel partners, and since we would like to uh, act as a bridge between academics and institutions where students might not be aware. Okay, we are learning these topics like we are learning a full wave rectifier, but where are they used? And what is going to be the response? We have everything on textbook, but how to check or how to cross verify whether what is given in textbook is exactly the same, or we can get the same result or not? If yes, how? Okay, so for that sort of comparison learning, we act as a bridge between industry and the institution. Okay, and we also help the students to illustrate what is there in the textbook. Okay, we at India for Technologies, we do that, and for that we conduct or we um, have regular training programs both online as well as offline. Because of this pandemic situation, we right now we have only online training programs, and in future, once the pandemic situation comes to an end, we'll also do offline training programs. Okay, uh, now let us move into the topic, AMS design flow. Okay, so for understanding this flow chart, before we understand this flow chart, we should have an idea of what is an analog design flow and what is a digital design flow. Okay, only if we have an idea on those things, we'll be able to understand this flow chart. Okay, so let us move into that part. So analog or full custom IC design flow starts with a schematic entry. Okay, before we move into schematic entry, or before we get the tools on get the circuit on the EDA tool, it is always better, or it is always important to work everything on paper. Okay, to work everything on paper. Once it is done, okay, once you have the results on paper, you are just going to cross verify, or you're just going to compare whether the results that you get on the tool and whatever you have on paper are matching with each other or not. Otherwise there is no use in going for the EDA tools, right? So that is where we first work the design on paper, but based on what we work, based on the results from market research analysis. Okay, because market research analysis will have, or will interact with the customers very closely. Okay, it is because of that interaction they get the data. Okay, and that sort of data will be passed on to the designers over here. Okay, so what are going to be those data? For example, just imagine that you have an air conditioner. Okay, and you hear like in order to reach a temperature, okay, room temperature anyway will be around 30 degrees Celsius. In order to bring the room temperature down to 20 degrees Celsius, okay, so whichever air conditioner does that quickly is considered as most efficient one, right? So market research analysis will have a data of how long it takes for an air conditioner or to bring the room temperature down from 30 degrees Celsius to 20 degrees Celsius. So this is just an example. Okay, and in order to achieve that, what is to be done? Okay, what is the timing provided by other providers? Because in whichever field you go, you have competitors. If you just go for an air conditioner itself, you have uh, Samsung, Onida, Panasonic. You have different brands, right? And right, you compare the results, and we should be well aware, well ahead of them. Okay, only then customers will prefer that particular brand. Okay, so how to achieve this? This is the data. Okay, I need to achieve or I need to bring down the room temperature from 30 degrees Celsius to 20 degrees Celsius within short duration, say around within 5 minutes. Okay, for example, so what should be done? Okay, how to get the design? Okay, and in case if you are bringing the temperature down, what is the current temperature? Okay, in which mode should you set the AC? You have different options, right, to bring the temperature down. So which option should be considered? Okay, and what will be the temperature? How to know the temperature? How to have an idea on the temperature? Okay, well, and once you achieve 20 degrees Celsius, it has to be maintained along that temperature itself, right? So how to do that? Okay, so for all those process and to get all those data, you need a market research analyst, okay, who can get you all the data. A designer cannot go out and market and keep on collecting the data. Then he lose time on completing the design, right? So you have people who work very close with the customers. Okay, so they get the data for you. Once you get the data, you work on a circuit to achieve that particular result. Okay, you first work on paper and then capture everything on the tool. Okay, so that is the process we call as a schematic entry. And the solution provided by Cadence for schematic entry on full custom IC design flow is Virtuoso Schematic Editor. And then you move into the simulation process. So what do you do here in simulation? You do two processes. First, you check whether the circuit is responding or not. Okay, you design the circuit, you give an input, and you try to check certain output. You try to get some output. Just a second. That's so you try to first you try to figure out whether the circuit is responding or not. Rather than looking for the correct results, first you should have an idea whether the circuit is responding to that particular input or not. Okay, once you find or once you figure out that the circuit is responding, you move into the next part. Okay, next is whether the circuit is uh, giving you the correct result. Okay, so that is why we call as functional simulation. Okay, functional correctness of the design. Okay, and for that you have a tool called multi-mode simulator, and the Spectre is a simulation engine which does the simulation for you. Once you have completed or once you have cross-verified the results provided by Spectre, and once you figure out that they are correct, or once you get the expected results, you move into the next step, which is layout part. Okay, layout in the sense you try to design the circuit and you mention certain physical parameters. So what do you mean by physical parameters? If you go for a MOSFET, metal oxide semiconductor field effect transistor, okay, you have dimensions like length and width, right? So those are the physical properties. Those are called the physical properties. So when you are working on schematic capture, you work on the symbolic representation of the devices. I think you should be aware of the symbolic representation for a MOSFET, for a resistor, for a capacitor, etc. Okay, so when you go for schematic entry, you will be working on the symbolic representation of each and every device. Okay, but how does that look like on a fabricated IC? What kind of view does it have on the fabricated IC? Layout gives you that idea. It provides you with physical representation of the circuit. Okay, it provides you with an idea of physical representation of the circuit. Okay, so once you are done with the layout, you move into the verification process. You need to cross verify, right? Whatever is there in schematic should be there in the layout. Only then it is meaningful, otherwise it is meaningless. Your layout is meaningless, right? So for that purpose you have physical verification. Okay, and you start with DRC. DRC stands for design rule check or design rule components. What do you mean by design rules? While designing any type of circuit, okay, nowadays you work on certain specific technology mode. Okay, so each and every technology node will have different layers, because when you go for a MOSFET, you need a metal, you need a polysilicon, you need contact, you need implantation. Okay, that is what will be available in the fabrication process, right? When you go for fabrication. Okay, so each and every technology node will have their own set of design rules, like size and spacing. If you are going for a metal layer, minimum size in order to have the conduction, okay, or flow of charge carriers, you need a minimum size and spacing. Okay, if you have any size less than that, then you don't have a proper connection, or you don't have a proper response. Okay, so for that you should have certain set of design rules, otherwise you don't have any connection, or you have a short circuit, or there is a breakage in connection. Okay, so for that purpose you have certain design rules specified by the foundry. Okay, So that is what that is the process we call as DRC. Okay, and then we have something called LVS. So LVS stands for layout versus schematic. Okay, so what is layout versus schematic? As we have seen already, okay, you have completed the circuit on paper and then you have captured it on EDA tool. Okay, whatever devices you have made use of or whatever connections you have made between the devices should get reflected in the layout also. Otherwise there is no meaning, right? There is no correlation between the schematic and the layout. Okay, so in order to cross verify whether uh, the schematic and layout are similar, okay, we go for layout versus schematic. That is the second step in physical verification. And for these physical verification process, you have a tool called Ashura. Ashura is for higher technology nodes, whereas PVS, physical verification system, is for lower technology nodes, say for technology nodes less than 45 nanometer, 45 nanometer and below. Okay, and then you go for parasitic extraction. Okay, so based on the layers and its dimensions, okay, you have certain parasitic devices like resistors and capacitors getting generated or getting created in the design. These devices, okay, why are they called as parasites? Because they depend on something else. Okay, they don't do anything on their own. Okay, they depend on something else in order to do the work. Okay, and they are not physically present here in the ICs, but when you check in reality, okay, for example, mushroom is a parasite because a mushroom cannot prepare food on its own, right? It depends on other plants for its food. Okay, so that is the meaning for parasites. So same way, depending on the dimensions of on layers, or depending on the overlap, or depending on two layers that are getting connected with each other, you have various resistors and capacitors getting generated, and these are called parasites. To check the impact of those parasites, you do a process called back annotation. Okay, so what do you do in back annotation? You extract the devices, okay, like parasitic resistances or parasitic capacitances. You extract them from the circuit. Okay, once you extract it, you'll get a netlist out of it. Okay, and that netlist is going to be made use of in order to import it into the schematic. You go back to the schematic, re-simulate your design along with these parasites. Okay, and if and you can by this process, once you do the once you simulate it again, you uh, get an idea on the impact of those parasites. Okay, so how do you check that? You can go for delay calculation. Okay, you can check the delay between the input and output. Just cross verify the results, simulation results, uh, with whatever was done before layout and after layout. So we call as pre-layout and post-layout simulation. Once you are satisfied with the results, okay, what you can do is you can go for the next level of process. Okay, in case if you are not satisfied, you don't get the expected results, you can rerun the simulation. Okay, or you have to work on the design once again, whether it is with the theoretical concepts or it is with the layout. Okay, so by this option, okay, you can optimize your design. Okay, and once you are satisfied with that result, you can go into the GDS file generation. So GDS stands for graphical data stream, and II stands for information interchange. So what does this give you? GDS file will give you the details of or layer map of the layout. Okay, whatever layers are available, dimensions, and how are they going to be located on the circuit, which technology node is used, and according to each and every technology node will have its own layer map. Okay, or mask. Okay, so having an idea of those things, so you cannot directly send a layout to the fabrication unit. So this file takes care of that details. Okay, this binary file will have all the details of your layout, and you can uh, send this file to the foundry to tape out your design. Okay, so Virtuoso will provide you with that kind of process. Okay, it will help you in generating that particular file. So any doubts till now, participants, in full custom IC design flow or uh, the tools that are provided by Cadence? Any doubts till now, participants? If you have any doubts, you can drop them on the chat box, or you can unmute yourselves and let me know about them. Any doubts till now, participants? So I can see something on the chat. Okay, so Vinod Kumar says no doubts. Any other doubts, participants? Okay, so I don't get any other responses. Meanwhile, if you have any queries, you can drop them on the chat. I'll take care of it during the QA session. Okay, so these are about the solutions provided for full custom IC design flow. Okay, now the next one is the semi-custom IC design flow. Okay, so this is the flow chart, and on either sides of the flow chart you can see the tools that are made use of for each and every process. So similar way, you get the result from you get the report from market research analyst, and you have certain data with you. Okay, you have certain data with you. Based on the data that you have, okay, based on data that is available on hand, okay, what you do is you start uh, creating the design. Okay, an RTL level design using any one of the HDL languages, hardware description languages. Let it be Verilog or VHDL or System Verilog or System C, etc. Okay, so once that is done, once your coding is done, you go for the functional simulation. Okay, so what do you do in functional simulation? You have three steps over here, right? Compilation, elaboration, and simulation. So you start with compilation. What is compilation? You have written a program. Okay, right, like you have written a Verilog. You have written a Verilog program. Okay, you have certain set of rules for writing a program, right? So those are called syntax. Okay, so checking for syntax and semantics in a program is what we do when you go for compilation. And the next step is elaboration. So what do you do with elaboration? You write a program, and in that you mention various logics, right? Like uh, an AND gate, a flip flop. Okay, uh, So how does the tool understand its functionality? How does a tool understand the functionality of a NAND gate? So for that, it needs certain libraries, right? So Cadence provides you, or Incisive provides you with those libraries, and once you run the simulation, okay, once you compile the design, okay, you go into the elaboration process in order to map your design with the library file. Only then you get the expected result. Okay, so how do you get the result? By doing a simulation. Okay, so for a functional simulation, you have two options over here. One is you can force the input values, or you can mention the input values in the form of a program. Okay, and they are called test benches. Okay, so using test benches, okay, you can check for the functional behavior of the design. The tool that you make use of for all these process is Incisive. Okay, so once you have checked out the functional results, okay, once you have checked for the simulation results, you move into the next process, which is called synthesis. As I have already told you, okay, the you have written a program, but how to check it, check its functional behavior, or how to have an idea of what devices formulate this circuit. Okay, so for that, uh, go for synthesis. Okay, synthesis in the sense you translate the program, okay, into a block level or module level design. Okay, you translate the program into, or design into, a block level or module level design. Okay, so in case if we have a NAND gate, how does it look like? You have a symbolic representation, right? Right. So NAND gate, in the sense, you may have a two input NAND gate or a four input NAND gate. So how does that look like? Okay. So these type of mapping can be done in synthesis. Okay. Convert the program or RTL into uh, block level or module level design. Okay, and then you go for timing simulation, right? The timing simulation, in the sense, uh, you need to, when you have interconnections between two blocks, right? So you need to have an idea about the delay elements also. Delay elements, in the sense, it can be a slack, it can be a slew, or it can be a rise time delay, or a fall time delay, or net to net delay, gate to gate delay. So for to cross check all these aspects of the design, okay, you go for timing simulation. And it is once you are doing it for the circuit, after completing your layout or after the physical design, uh, then it is called sign off, timing sign off. Okay, and in case if we are working for the power analysis, that is static power dissipation or dynamic power dissipation, then it is called as a power sign off. For timing sign off, you have a tool called Tempest, and for power sign off, you have a tool called Voltus. Okay, and then, as I have told, we go for a reliability check. So what is a reliability? Let me give you an example. You buy a mobile phone today, okay, and at the beginning it works faster, because you won't have any data, or you won't have any contacts, you won't have any images or video files, etc. But as you start using it, say after a week, okay, if you check about its performance, there won't be much of a difference. Next, after a month, there won't be any much of a difference. Let us check its performance after a year. Maybe your memory might be full, or you might have recorded more videos or audios. Okay, and because of those aspects, because of those files like a video file or an audio file, the performance of the circuit or the performance of the design should not get degraded. Even if it degrades, you should have an idea of why it's getting degraded. Okay, so this is what we call as reliability. Okay, a device that is working well today should give the same sort of response even after 5 years, because you spend thousands of rupees on purchasing a mobile phone and you don't wanted to replace it, or you don't wanted to change it uh, within a month or within a year. You look for long-term usage, right? So that is why we go for a reliability check. Okay, once you have an idea about that, once you have an idea about the reliability check, and you also uh, go for something like faults. Okay, fault determination or fault testing, because after fabrication you cannot assume like the circuit will provide me the expected result. 99% of the circuit doesn't provide you with the expected results. There will be changes. Okay, in case if you have those changes, what are those? Okay, and why are we getting those changes? Okay, is what we do, or is what we identify uh, by doing a DFT. Okay, for example, you have something like stuck at zero fault or stuck at one fault. For example, you have designed NOT kit. Okay, you have fabricated a NOT kit and you want the output to remain in zero for 20 seconds. If 0 is an input, the output also should remain in 0 for a duration of 20 nanoseconds. After 20 nanoseconds, it has to move into 1. Okay, so this is what we call as stuck at 0 fault. I'm just giving you an example, but that is not the correct. Just giving an example, real-time example of what it is. Okay, similar to that, you have stuck at one fault, built-in self-test, etc. So inducing these fault mechanisms and check its behavior. So this is mainly for verification purpose. Okay, once you are satisfied with these results, you move into the physical aspects of the circuit, physical representation of the design. Okay, so for that you have a tool called Innovus. So what are the steps involved in physical design? You start with a floor plan. Okay, you have a floor planning process, and then you move into power planning, placement, clock tree synthesis, and routing. Now, what is floor planning? I'll give you an example. If you are planning to build a house, okay, you buy a piece of land, say for uh, 800 square feet. Okay, you have a land of 800 square feet and you are planning to build a house. So first you decide upon the area for each and every space. For example, kitchen should be spacious, so it should have it should cover a space of so and so square centimeter. Okay, or so and so square feet. You leave some space for parking area, you have some space for living room, you have some space for dining room. Okay, so this is what we call as floor plan. Similar to that, you work on the design also. In your design, you decide upon where should I have the power ICs, where should I have my uh, input ports, input output ports, and what should be the spacing between each and every port. Okay, how to establish connections between the ports. Okay, so this is what we call as floor planning. Okay, and then comes power planning. Okay, I have decided as of this much area should be occupied by my design. Okay, uh, but after that you need to have the power lines, right? Supply and ground, or power and neutral. Okay, so how to get that? What should be the thickness? What should be the spacing? And what kind of material should be made use of in order to get your power lines? Okay, so that is what we decide with the power plan. Once power planning is done, we go for placement. Okay, so you have got the entire design, but how to get it on paper or get it on silicon? Okay, so that is the process. Placement process helps you in getting your design onto silicon wafer. Okay, and once you have all the blocks, you have something like input blocks, or especially for sequential circuits and combinational circuits, you will be having clock signals. For sequential, you'll be having clock signals. For combinational, you don't have the clock signals. Okay, so how to get that introduced to the design is why we go for clock tree synthesis. Once the clock tree synthesis is done, okay, you go on for final routing, overall routing of the design. And for that you have a process called, or completing the interconnection between all the blocks available in your design. That process is called the routing. Okay, and the tool used for all these steps, 5 steps, you have approximately 5 steps, right? The tool that is used for all the steps is Innovus. Okay, gives you an idea of the physical representation of the design. Okay, so that is what that is why we go for a routing process. Okay, so once routing is done, you move into the next step, physical verification. uh, Explanation for this is the same as you have for full custom IC design flow. Okay, uh, you have certain design rules, and you need to cross verify or make sure that you have followed those design rules. Otherwise you have some losses, power dissipation, or you have some interferences, like you talk about electromagnetic interference, EMI and EMC. Okay, how to avoid that and why do we get that? Okay, so all these data you get when you go for design rule check, and layout versus schematic, as you already know, is a comparison of your schematic and the layout. Okay, both should have the same results. Okay, and then you have the parasitic extraction. Because of layers and its dimensions, you have some parasitic resistances and capacitances getting generated. Okay, and extracting or having an idea about those parasitic elements is what we call as RC extraction. Okay, RC extraction, and for that we have the tool PBS or Assura. Okay, PBS or Assura. The same thing as we have used for the full custom IC design. And then finally, we generate the graphical representation or binary representation of the circuit. Okay, so for that is what we call as GDS2. And to generate all these data, you have the tool called Innovus. And by using Innovus itself, you can generate the binary file, or what we call as is a layer map file. Okay, which has the details about the layers, where each and every layer interconnected, which is the top cell, etc. Okay, So when you are working on a mixed signal design, okay, you have to undergo both these steps. Okay, you have to undergo both these steps. How and why, okay, is what we'll be checking out during the demonstration process. Okay, so first let us have a look at the flow chart of AMS design flow. Okay, so as I have told you, you have two options. Either you can have an analog module as top level design or top cell, or a digital module as a top level design or top cell. Okay, so in both the cases, how it can be done. We have already seen the flow chart for full custom and the semi-custom IC design flow, but how to get both of them together is what we are going to check out on Cadence. Okay, so any doubts till now, participants, on the design flow, full custom IC design flow, semi-custom IC design flow, and AMS design? Any doubts till now?
Participants, if you have any doubts till now, means you can ask.
Let me open the chat box also. So Vinod Kumar sir says no doubt. Any doubts till this point, participants?
Sir, I think there is no doubt, sir. You can continue, sir.
Okay, so let me move into that process. Okay, as of now, because of timing constraints, what we'll do is I'll show you as of how to create a schematic, okay, on Cadence. Okay, how to create a schematic on Cadence, and how to import a Verilog file into Cadence, how to combine both these analog block and digital block, how to verify the results. Okay, this is what I am going to do now. And for this demonstration, what I'm going to do is consider a, an inverter. Okay, inverter in both the cases, and build a buffer circuit. So buffer in the sense, whatever you give in the input should get replicated at the output also. Okay, so for building this buffer, I'm going to make use of inverters. One is going to be CMOS inverter, and the other one is going to be HDL based inverters. So let us see how to do it. And for that, I'm going to make use of the tools like which is so Spectre and AMS. Spectre and AMS are going to be the simulation engines. Okay, so let me go into Cadence tool. Okay, so before I start capturing, the schematic capture, I need to create a workspace. Workspace in the sense a folder, because whatever log files are generated for each and every design, okay, should remain separate. Okay, so for that purpose, I create a workspace, nothing but a folder. To create a folder, I just go for a right click and go for create folder. And the OS that is made use of here is Red Hat Enterprise Linux, because Cadence is supported only in ARCHE-FDP. No other operating system supports Cadence, and even uh, in the must list or in customer requirement list provided by Cadence itself, it would be mentioned. Okay, so I'll name the folder as Kungunadu. Okay, click on enter so that it gets created. Okay, and then you need to open this folder. You need to enter into this folder so that whatever log files get generated or your overall design will be available within this workspace. Okay, now I'll open a terminal. Okay, and initialize the shell script. Initialize the shell script. Initializing the shell script in the sense, uh, you have certain libraries in common for both Cadence as well as Red Hat Enterprise Linux. Okay, and Everything are mapped together in the form of a shell script. So you need to initialize that. To initialize the shell script, I give a command called CSH. CSH stands for shell. Okay, and then source a file called CSHRC. Okay, so CSHRC stands for shell script run command. Okay, CSHRC stands for shell script run command. So what does this consider? This consists of? CSHRC file consists of the tool installation directory. Okay. CSHRC consists of the tool installation directory for each and every tool provided by Cadence. Details. Okay, details of the tool installation directory. And the next one that the CSHRC file has is from where should the license be fetched. Okay. Or from which machine should the license be fetched. Okay, so CSHRC file consists all those details. That is why we are initializing or we are sourcing the CSHRC file. So once we source the CSHRC file, okay, so excuse me. Let me open the terminal once again. Initialize the shell script and then the source the CSHRC file. Okay, so once you source the CSHRC file, you'll get the icon like this. Welcome to Cadence Tools. So under Cadence, you have n number of tools, right? Virtuoso, Spectre, AMS, Incisor, Innovus, Tempus, Voltus, etc. So among them, which is required as of now? Right now, I need to capture a CMOS inverter, right? So for that, I need Virtuoso. So I'll type Virtuoso space ampersand. Okay. You can also invoke the tool without giving an ampersand. By giving an ampersand, you get a command. Okay, like this. Even if you wanted to execute some other commands, you can do that. Okay. So I'll maximize this. This is my command interpreter window. Okay, this is my command interpreter window where I have a view of all the errors and warnings as a result of each and every process. Okay, and then what I do is I go into tools and select library manager. Okay, in my library manager, I have three columns. One is library, cell, and view. Okay, so under library, what you can see is the predefined libraries provided by Cadence itself. Okay, along with the technology node. Okay, you can see 45, 90, and 180. GPDK 180, GPDK 90, GPDK 45. Okay, 45 nanometer, 19 nanometer, and 180 nanometer technology nodes, which are not foundry standard. You cannot fabricate an IC by designing the circuit using any one of these technologies. Okay, it is only for learning purpose. Okay, so if you select any one of these libraries, you can see the devices or components that are available in this. Okay, so for example, GPDK 180 consists of all these cells. GPDK 90 consists of all these cells. GPDK analog lab has all these devices. And these devices are called cells. Okay, if you select any one of these devices, you can see the library files available for these devices. For example, a symbol, Spectre supported library. Okay, Spice supported library. Okay, so like this, you are going to create your own library. You are going to have some cells within that, and you are going to create views for each and every cells. Okay, so let us see how to create the library. So what I'll do is I'll go for File, New, and select Library. Okay, mention a name. So I'll name it as one underscore buffer. Okay, because I am designing a buffer circle. So I'll mention one underscore buffer. Click on OK. And at the bottom, you can see technology library. Just select attach to an existing technology library and select OK. And select OK. And you can see the list of technology libraries. Select any one of them. Like I'll select GPDK 180 and select OK. Fine. Now what happens is I get the library created over here. Okay. So if you select the library, you don't have anything because you haven't included any cells or you haven't created any cells. But how to create that? To create a cell for this particular library, what I'll do is I'll select the library, go to File, New, and select Cell View. Give a name for the cell. I'll give a name as uh, INV underscore design. Okay, inverter, design, and select OK. Right? So you have the schematic editor. Okay. So for a CMOS inverter design, okay, I need CMOS in the sense I need an NMOS transistor as well as a PMOS transistor. Okay, MOSFET. I need complementary flavors of the MOSFET. So for that, uh, I'll go for instance. I have already told like each and every device is called as an instance in the schematic. To add an instance in the schematic, what you have to do is because I have chosen the technology node to be GPDK 180 nanometer technology node. So from the library, I'll click on the drop down and select the technology node as GPDK 180. Under cell, you can also click on the drop down and select NMOS transistor. Okay, or you can just type it. Okay, so if you select NMOS transistor, you can see the parameters, length, width, etc. As of now, since it is only a demonstration, I'm not going to change anything. I'll take the default values. But if you want, you can change it. Okay, so I'll go with default values as of now. So I'll click on hide and I'll place it over like this. And similarly, I need a PMOS transistor. Again, I'll go for add instance. Just replace this NMOS as PMOS. Okay, click on tab and you can see the parameters. Just I'll click on hide and place it over here. I've got both the transistors, okay, but I need the input and output pins. Only then I'll be able to interconnect, right, with other cells. So for that, I need input and output ports and include pins for that. Okay, so I'll go for create and select pin. Okay, so for that, what I'll do is I'll name all the input and output pins. First, we'll go with input pins. So A is going to be the input port. VDD and VSS are supply and ground, right? So those things are also going to be considered as input ports. So I'll choose VDD, click on hide, and I can place in the same order. You can create n number of pins at the same instance, but separate them with spaces. Okay, that is what we have done. And place the pins in the same order. You can also rotate the pins using the shortcut R. Okay, and then I need an output port, right? So I'll go for add pin again. Give a name for the output port and choose the direction to be output. Okay, so here if you click on the drop down, you have the options. So I'll select output from that. Click on hide and place it over here. Now use wire to complete the interconnection. Okay, so the shortcut for wire is W. Just click on W on the keyboard. Make a left mouse click at the starting point and left mouse click at the ending point. Okay, so like that, I'll complete the connection. Okay, in the same manner, I'll complete the connection. Okay, like this. Fine. So source and bulk of PMOS is getting connected to VDD. source and bulk of NMOS is getting connected to ground. And drain of PMOS and NMOS transistor are getting connected to the output port. Gate of PMOS and NMOS are getting connected to the input port. Okay, so once the schematic capture is done, okay, you have to check your design. Okay, you can also check if there are any floating nets or if there are any floating terminals or floating devices. Okay, and save it. Okay, so for that, what we'll do is I'll go to file and select check and save. Okay, or you can just go for save. I'll go for check and save. So how to check if there are any errors or warnings in your design? So you can go to command interpreter window, which you can see at the bottom, and go for and check the last two lines. In the last two lines, you can see the schematic. Okay, you can see whatever is there in case if there are any errors or warnings in the schematic, and then you can go ahead. In case if you have any warnings, then it will be listed out over here. Okay, so your schematic capture is done. Okay, now you can create a symbol. Okay, a top level hierarchy, so that you need not um, capture an NMOS transistor, PMOS transistor in different cells. Okay, just you can call the symbol and just you can make use of it in the circuit. Okay, so for creating a symbol, I'll go for create. Under that, select cell view, and under cell view, go for from cell view. Okay, so you can see library name, cell name. From a schematic, you can create a symbol. Okay, and you can select OK. You have the pins. You have the options of deciding the pin location. Okay, so on left hand side, I'll have my input pin alone. So I'll remove VDD and VSS. On right hand side, I'll have my output pin alone. On top, I'll have the VDD, and at the bottom, I'll have the VSS. Okay, so now you can click on OK. Right. So this will be the default symbol. In case if you wish to create your own, like for an inverter, you have a triangle and bubble in front. Okay, so I'll remove this inner rectangle. Okay, and use create line option. I will select the create line option and create a triangle. Okay, I'll create a triangle and you have a bubble. Okay, so for creating a bubble, I'll go for create circle option. Okay, so like this, you can create the symbol for an inverter design. Okay, or any other design also for an amplifier, or an AND gate, a flip-flop, whatever it is, you can create a symbol, top level hierarchy like this. Same thing, after creating the symbol, just go for check and save. Okay, so in our command interpreter window, you can check if there are any errors or warning. So you don't have any errors, right? So close the circuit. Okay, now I need to check its functionality, right? So in this, in the library that I've created, I have now created a cell. Okay, and for this cell, I've created a schematic view and a symbol view, right? Now I need to check whether it is working fine or not. Inverter in the sense, if I give 0 as an input, 1 should be the output, right? So how to check that or how to cross verify that? So for cross verifying or to check the functional behavior of an inverter, I'll again go back to file, new, and go for a cell view creation, right? So for give a different name now, because just imagine that you have created a folder in Windows itself, in any of the drives, say in a D drive, you have created a folder. Okay, within the same folder, within the folder, can you have two Word document of the same name? You can't, right? Or two PDF files of the same name. You need to give different names, right? So like that. I'm creating another cell, and for that I'm giving a different name. Okay. So give a cell name and select OK, right? So go for add instance, and I'll go for buffer. I'll select the library because within the library only uh, I have the symbol that I created, right? So I'll select the library and select the cell which has the symbol. Select the cell which has the symbol, click on hide and place it over here. Okay. Now I have got the symbol that I have created. I need to test this. To test this symbol, I need an output port because I need to check the output, right? I need an output port. I need a ground terminal which has to be connected to VSS, and I need a voltage source to have a supply VDD. Okay, and I need some sort of stimuli. For example, if I need a unit step stimuli, I need a source for that. Okay, let us see how to do that. Okay, so for an output port, okay, for including an output port, I'll go for an add pin option. Okay, give a name for the pin. Okay, so what is the name? I can give a name as v underscore out. Okay, click on hide and place it over here. Okay, next I need a ground terminal. I'll go for add instance again. So devices like ground, supply, voltage, as well as stimuli, all these things will be available under the library called analog lib. So devices, all the devices available under analog lib are technology independent. Okay, they are general devices, can be used across any technology. Okay, so I need a ground terminal. So I'll just search, you can just type GND. Okay, so that you can see ground terminal. Okay, so I select one, click on hide, and you can place it over here. Okay, now I need an input stimuli, right? So again, I'll go for add instance. Okay, and select a source. I need a step stimuli, right? So I have a pulse source. I'll select the pulse over here and give the properties for the pulse. Okay, I need a train of pulses. Uh, so for those pulses, logic 0 will be represented by 0 volt, and logic 1 will be represented by say around 3.3 volt. Okay, 3.3 volt. And then I'll have the train of pulses for a period of 20 nanoseconds. Delay time will be 10 nanoseconds. These are just values that I'm assuming. For rise time, 1 picosecond. For time, 1 picosecond. Pulse width should be half that of period, right? Either 50% or more than 50% of the period. So I'll give the pulse width as 10 nanosecond. Click on hide and place the source. And then I need a DC source for supply voltage, right? So the DC voltage value that I'll take is 3.3 volt. Click on hide and place it over here. Okay. I need ground terminals for these two also, right? So I'll select the ground terminal from here. We know how to instantiate it. Let us see how to copy it. Okay, I'll select it. Go for the bind key C. Just click on C in the keyboard. Just make a left mouse click and drag. So you'll get a copy of the ground terminal. Again, I have selected copy, okay, and paste. Okay, now use wire to complete the connection. Use wire to complete the connection. Okay, so this is what we call as a soft connection. Let me show what is soft connection. I'll just get an extended wire from a terminal, any terminal, okay, whichever you wish to do it as a soft connection. And just get an extended wire, okay. So whatever we do here, we have done here is hard connection. The ground and the terminals are connected directly. Okay, so for soft connection, I'll use labels. So for creating a label, I'll have a shortcut L. Okay, L for label. So I'll go for L and I'll give a name for the label. So first one for input stimulus. So I give it as a in, and I need two. One at the source and another at the symbol. Okay, so I'll mention a in twice. Okay, and you can instantiate any number of net names at the same instance of time by separating them with spaces. Okay, and then I need VDD. Okay, click on hide and place them. You get a dot, right? So connect the dot to the wire so that the particular net will be named as A underscore in, okay, or VDD, whatever it is. So here I'm not placed it exactly on the wire. Okay, so I now go with limits. Okay, you can also select it and drag and drop. Okay, you can just select and drag the net. Okay, so now the schematic is completed. Test bin circuit is now ready. Okay, go for check and save. If I go back to the command interpreter window, I don't have any errors or warnings. Okay, now let us see how to run the simulation. I'll go for launch, select ADEL. Okay, and before you start running the simulation, first you need to have a look at the model libraries. Okay, for each and every cell that we have designed, we have certain library files based on the simulation engine that we make use of. Okay, so first we have to make sure of that simulator. So here we have Spectre as a simulator, that is fine, and then model libraries. So I'll go for under setup, I'll go for model libraries. So you can see the technology node 180 nanometer and its respective SCS file. .SCS stands for Spectre Circuit Simulator. And in case if you need to do the simulation for certain processing corner like nominal or typical, slow corner, fast corner, you can do that. Okay, so I'll select nominal, click on apply and select it. Right. Next, you have some analysis to do. Okay, if you are interested in doing time domain analysis, so you can go for analysis, and go for choose. And for time domain analysis, it is transient, right? So I'll select tran, and I'll mention the stop time. For example, I'll mention the stop time as 100 minutes. I'll go for accuracy defaults as moderate. Okay, moderate level of accuracy. Just I need, because since we are going for time domain analysis, at each and every timing instance we have the value of voltages. We have different values of voltages or same values of voltages. So how to capture them? Okay, different timing instances, in the sense it is for different, it is for discrete timing. Okay, discrete timing analysis. Okay, so discrete instances of time. So I'll select moderate for that. Conservative in the sense more number of timing instances will be considered for analysis. So the results will be accurate. Okay, liberal in the sense considerably lesser number of timing instances. And this will be done in the random manner because you have certain algorithm running in the background for that. Okay, so click on apply. Soon as you click on apply and select OK, you can see the types of analysis that you have chosen. Okay, so transient analysis you have chosen. You have mentioned the parameters for the transient analysis. Okay, now you need to select the signals that have to be plotted, right? You need to plot the input signal and output signal to cross verify the functionality. So for that, I'll go for outputs and select setup. Okay, so click on from design so that you can select the input net and output net from the design. Okay, now we can go back to setting outputs tab at the bottom, click on OK, right? So what all signals have to be plotted gets included in the output stack. Okay. Now you can run the simulation. To run the simulation, what you can do is you have the option called netlist and just make a click on that. Okay, so that you can see the simulation. That's it. You can see both the input and output signals merged with each other. Okay. To split it up, you can go for graph and select, sorry, graph and select split all strips. So you can see the signals. First you have the output signal and then you have the input signal. You can just rearrange the signals. Okay, you can select the output signal and just drag it to the top. You can also change the signal properties. So I'll select both the signals, make a right click. I'll go for style. I need a solid line. And then in case if I wanted to change the width, I can change it. You will have better readability or better visibility. In case if you wish to change the background also, you can do that. Just make a right click and go for its graph properties and you can change the background color. Okay, right? So this is how you run the simulation for an analog design. Now you need to import an RTL design into Virtuoso, right? So let us see how to create the file as well as how to import it. Okay, so I'll close this. Okay, I'll close the log file. This is the log file. This is the simulation state. I need not have this. Okay, because I have checked the results. Okay, so I'll close this also. And before closing, I need to save this. Okay, for the verification purpose, I'll save this state. I'll go for yes. And I've done everything for a cell view, right? So save state option and select cell view. In case if you wish to change, save, give a different name for the state also, you can give inverter underscore state. Okay, and select OK. So the state gets saved now, and I close this also. I need to include a .b file within this. So for that, I'll have to first create. Let us see how to create a .b file. This is the folder that we had created already. Okay, so from this itself, I'll open a terminal. Okay, I'll create a .v file. So for that, I need some text editor, right? So I'll go for gedit. Gedit is a simple text editor, just like Notepad and Windows. We have most basic and simplest text editor, gedit, space, give a name for the file. Okay, I'll name it as inv.v. Click on enter, you get a text editor open. Okay, first one is I need to give a module. Okay, I need to create a module and I need to give a name for that. Okay, so I'll name it as inverter, and within that I need to mention all the nets, input ports and output ports. Okay, and then I'll assign an input port, assign the input port, and then assign the output port. Okay, and then give an expression, assign y is equal to what is going to be the functionality. Okay, negation of a, right? So I have created the functionality of an inverter and then end module. Okay, in the module. Once this is done, I'll save the design. Okay, I'll save the .v file and I'll close this. Okay, we have got it, right? Inverter dot. So if you close the terminal, you can see the .v file over here. Okay, now let us see how to import this into Virtuoso, right? So I can see the command interpreter window over here. Okay, I need to import the .v file, Verilog file, right? So I'll go for file. Okay, and under file I can see import. Under file, select import, and for that I'll go for Verilog. Okay, So you can select the .v file to be imported. Okay, Verilog files to import. I'll just go for browse. From the workspace that I created, I can select the .v file. Okay, I've selected the .v file. Click on open. So within which library should I import? Within one underscore buffer, right? So I'll go for browse and select one underscore buffer. Okay, and close this. That's it. So what are the modules that you are going to import? I'm going to have a schematic. I need to create a functional view, and I need to create a symbol view for the inverter. Okay. So just I have made sure of those things. Click on OK. So what will happen? I'll show you the log file to check what had happened in the background. So click on yes. So you can see Verilog compiler has been made use of for the syntax check. The program is compiled and then a symbol is created. Okay. And then a functional view is also created. Okay. So that is what we have done. So how to check whether these things are available or not? I can go back to the one underscore buffer, okay, library, because I wanted to be I wanted that to be imported over here, right? So I'll select this once again, and you can see this is the CMOS inverter where I have schematic and symbol view, and then I have the test bench circuit, okay, where I have the state and the schematic, and then I have the inverter out of a .p file. Okay, if you just make a double click on the symbol, you can see the basic symbol that has been created. Okay, and then you have the functional view where you can cross check the program. Okay, there you have there you can cross check the program. Okay, and then you can close it, right? So let us stop over here because we won't be having sufficient time to check how to interface both the blocks, and we shall discuss about those things in the next session. We have one more session between 2 p.m. and 4 p.m., right? So in that session, let us see how to create a next signal design, that is the buffer circuit, how to simulate it, and how to check the how to check the functionality of the blocks. Okay, so now we are into the question and answer session. Any doubts, participants, till now? Let me open the chat also. So in case if you have any doubts up to this point, okay, in your full custom IC design flow, semi-custom IC design flow, and the AMS until schematic capture on Virtuoso, simulation using Spectre, and then importing the RTL into Virtuoso. How we have done everything. Okay, so any doubts till now, participants? So I have the chat box open. In case if you have any doubts, you can let me know. You can type your queries on the chat, or you can unmute yourselves and let me know the queries.
Dear participants, this is the time for question and answer session. If you have any doubts, means you can post your question in chat box or else unmute yourself and discuss with our resource person.
Any doubts related to full custom design, semi-custom design, or mixed signal design, you can unmute yourselves and ask your queries, or you can post your queries on the chat.
Please, you can put in chat box.
Any queries, participants? And you can also give me your feedback about the session on the chat itself, because I don't think I'll be having a view of the online feedback. Okay, so better you can also give me the feedback about this session, so that during the next session we can clear those things out. If you have any specific queries also, you can post them so that I can try to answer them during the next session. Any queries, participants?
So thank you, sir. I think there is no queries from participants side, sir.
Okay, sir. Okay. So I would like to hear the feedback from them in case if there is.
Okay, sure.
Jagadish sir has given me a feedback. Thank you, sir. Thanks for your feedback. Anybody else? Or anything you want me to demonstrate, you can let me know. Like full custom I have demonstrated until the simulation process. Semi-custom design flow I haven't touched upon it. Maybe if you want me to demonstrate that, I can do. You can let me know. We are yet to complete the mixed signal design. We have just created an analog block, and we have imported a digital block within inside virtual. We have to see how to combine both the blocks and how to simulate it. Okay. Yeah.
Sir, I think there is no more queries or doubts from participants side, sir.
Okay, sir. Okay. Sure.
Let me wind up the session, sir.
Yeah. Yeah. Yes.
Yes, sir. You can join at 2 p.m., sir.
Yeah. Sure.
Thank you, sir.
So thank
Dear
you.
participants, the day 6 session one attends in the feedback link is posted in chat box. It will be open up to 30 minutes only, so kindly fill it, sir. And all the participants are requested to join the afternoon session at 2 p.m. sharp. Thank you. And one more information, while filling the attendance and the feedback form, kindly select your respective FTP ID. Thank you.
Thank you all. Thanks for your patience. In case if you have any queries, you can let me know during the afternoon session. Okay. Thank you all.
Thank you, sir.